Hi everybody, welcome to video number 1 of our Unit 2 on bonding video series where we start to take a look at chemical bonds. First, let's remember a couple things about some chemically unstable atoms like lithium and fluorine, and how they will change their valence electrons in order to gain stability by achieving a noble gas configuration. Lithium will do this by losing its outermost valence, thus achieving a noble gas configuration and becoming chemically stable. Fluorine will do it similarly, except it will gain an outermost valence electron, attaining a noble gas configuration and becoming chemically stable. What we left out was, how do these atoms do this? Lithium can't just lose an electron and fluorine can't just gain one. They have to go to and come from somewhere. The answer to this question can be found by understanding chemical bonds. This video will feature ionic bonding, just one way that atoms can attain this noble gas configuration. You're going to see how electrons are transferred from one atom, a metal, to another atom, a nonmetal, creating what we call a cation and an anion. Let's use lithium and fluorine as an example. Lithium isn't just going to lose that outermost valence, it's going to lose it to the fluorine. That's going to give lithium its noble gas configuration, making it stable. That's going to give fluorine its noble gas configuration, making it stable. Even more importantly is that these atoms now become charged. They become ions. Lithium with a positive charge we're going to call a cation. All positive atoms will be called cations. And fluorine with a negative charge we're going to call an anion. Even more importantly is, as Coulomb's law tells us, these two oppositely charged particles will now be attracted to one another. That attraction is the ionic bond. Like most things in chemistry, we need a way to model this process on paper. I'm going to show you one way to do that with sodium chloride as an example. You start off by simply drawing the electron dot diagrams for each atom. Sodium with 1 valence, chlorine with 7. Secondly, you draw arrows to show how the electrons transfer from the metal to the nonmetal. Sodium gives its 1 valence to chlorine, and then both have satisfied the octet rule. Finally, you draw what they turn into after this process is over. Sodium is now a +1 charge, chlorine with a -1, and you can even figure out which noble gas configuration they have and find the formula of the compound. Let's look at a more challenging example with magnesium fluoride. The process starts off the same. Electron dot diagram for magnesium with 2 valence, fluorine with 7. Start drawing arrows to show the electron transfer. Here's where the problem comes in. Magnesium gives 1 valence to fluorine. Fluorine becomes stable and satisfied, but magnesium still has 1 valence electron to get rid of. Whenever this happens, you simply add more atoms. If you needed more fluorines or more magnesiums, you could add them until everybody has been satisfied. With the second fluorine, that electron has a place to go, and the ions they turn into are an Mg plus 2 and 2. You have to show there's 2 fluorines, 2 F minus 1s. Here's the noble gas configurations they have, and the formula for this compound would be MgF2. Being able to model this process is a really important skill in any chemistry class, so I'd like everyone to pause the video, see if you can do this on your own using aluminum nitride as an example. Alright, here's what you should have. Aluminum nitride begins with this electron transfer and finishes with these ions. Pause the video if you need to take a look at this a little longer. We're actually going to switch into our second example. This is a little more complicated, calcium phosphide. Pause the video, see if you can do it on your own. Okay, here's what you should have for calcium phosphide. It begins like this, a lot of atoms going on, turning into 3 calcium plus 2s and 2 phosphorus minus 3s. If you need a more detailed look at how to solve these two examples, an extra video has been added at the conclusion of the tutorial. This extra video isn't required, but feel free to watch it if you need. That actually concludes our video on ionic bonding. Please enjoy the wrap-up to follow.